On the next lowest structure we got here, okay, I'm gonna do it a little bit faster than we did already because we already know on the first one on the class what was it. So in here you got the least electronegative. Even though phosphor and oxygen you have only one, phosphor is less electronegative than oxygen, and also it's on the left side. That would help you too. Sometimes it's the center, but most of the time the center atom, but most of the time is this one. So we got here, okay, let me erase this to do it here. We got here the central atom, and let's draw first the structure. You got 3Br, and oxygen. So valence is going to be phosphor 5 plus oxygen 6 plus 3 times 7. Okay, no F charge, so you don't have to add or subtract electron, depending if you have a positive or negative. So it would be 11 plus 21. It's going to be 32 electrons. So let's start placing the bonds as single bonds, okay? And it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It doesn't matter which one you start with. 4, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Perfect. Best Lewis structure, we don't know. We know already that the oxygens, okay, I'll go faster, but the oxygen, you can double check with one single bond and all this, the 6 unshare electron, the formal charge is -1. You know it already. Okay, we did it several times. Okay, so it's 6 minus 1, 2, 3, 4, 5, 6 plus 1, 7, 6 minus 7. On the bromine, let's do the bromine. Okay, we haven't practiced it. And it's 7 the valence minus how many on share? 1, 2, 3, 4, 5, 6, right? Plus 1. Basically, you want to put the halogens, which only need an electron, on the side, okay? So it's going to be 0. Now, on the phosphor, right, this we have 3 identical, so it's going to be 0, 0, and 0. So let's do the phosphor now, and which is going to be 5 minus 4 bonds. It's going to be plus 1. Okay, and this is plus 1. Can we go a little bit further? Let's do the charge, total charge, and it's gonna be, should be equal to 0. 0, 0, 0, minus 1 plus 1, 0. Let's try to get the central atom to 0. Now, double bonds on the terminal halogen is extremely difficult. Okay, because I remember how I said about the terminal atoms, the extend octet. Okay, but for phosphor is down on the third period, so you can have an um, extend octet. Let's check. Hold on, because I knew it already, so I jump it. Let's double check before the octet. 1, 2, 3, 4, 5, 6, 7, 8. This has 8, and this has 8. Yeah, it seems, but let's go further, even if you don't like it, to see if we have a best. And it's the what we can do here is make this a double bond, right? And to see what is our formal charge. So if we make here the oxygen, remember those 2 electrons that are here, we take them here to form a double bond. And here the bromines, let me get it a little bit higher, are gonna form single bonds, and they stay the same. And anyway, we don't need to touch them too much in this case because they have already 0. So try not to touch the ones that have already a formal charge of 0, because that's what we're trying to accomplish. So we got here the high bromine stays the same. Okay, 0, 0, and 0. And let's look at the ones that had a charge. Now, the formal charge different from 0, and it's going to be oxygen. Okay, and it's going to be 1, 2, 3, 4. So it's going to be 6 minus 4 plus 2, and it's gonna be 0. 6 minus 6 is gonna be 0. Oh, it looks like perfect. Let's double check. You need to do it. So formal charge of phosphorus would be 1, 2, 3, 4, 5, and it's gonna be 5 minus 0 lone pairs. Sorry, minus. I'm trying to go faster, so okay, minus 0 unshare electrons plus you got 5 bonds, and this is gonna give you 0. Okay, so 0. Oh, this looks like a perfect Lewis structure. I wish all of them will be like that. So 0 plus 0 plus 0 plus 0 plus 0, that is the total charge of a molecule. So you do your, no, you don't need to put the parentheses, sorry. Okay, so this is, now if you want, when you draw that Lewis structure, you can erase that, or you don't have to put it on the side, on them. If you want to leave it, for me would be okay, but you're not supposed to leave it like that. You're supposed to draw it again or erase them. So you got here your Lewis structure. Now let's look. Is that? That's it. Let's look, okay, at your shape, molecular shape, electron geometry, and polarity. You got one domain here, one domain here, one domain, and one domain. I got 4 domains. Okay, let's look at the shape electron geometry. Electron geometry, I put like that, would be, okay, 1, 2, 3, 4 is tetrahedral, 4 domains. Okay, 4 domains. Now, how many of them are atoms? 4. How many lone pairs of phosphorus I have? We're starting the central atom, 0. So the electron geometry would be tetra, okay, tetrahedral. And what would be the shape of the molecule? Molecular shape or molecular geometry would be tetra. Remember when we got 4 and 0 is tetra, tetra. Okay, now let's look at the polarity. Is it symmetrical? No, because one of the atoms is different. So the pull of this oxygen is different from the bromine, which is going to be higher. So it's polar. And now, by the way, you'll get the extra points. I wrote it on the announcement if you draw me the shape. So if for a tetrahedral, you're going to have the phosphorus. Okay, we can put whatever you do. You don't put a double bond, okay? And you don't put the lone pairs. So let's do it like that, how it is on the Lewis structure, but you have to draw it. Now you have to draw it with the shape. Bromine, right? And this one would be up front. Bromine, and this would be on the back. Some books draw it like that. Some draw it, I used to draw it like, now I'm drawing it like that. Now, if you look at this, right? Anyway, that's the 3D sketch and that would be all. But I want to show you something. If you look at the dipole moments, right? Where is it going? Bromine, more electronegative than phosphorus. So you would go this way, and this way. As this is a higher, okay, you cancel out these two, and this one is higher than this one. This is the difficult part about doing it like that. That's why I tell you symmetrical, it always gonna be nonpolar, because here this is gonna be pull more, so you're gonna have a net dipole moment, a net, right? Up here, how much is this? You need to subtract vectors. Okay, so let's do the following Lewis structure. Okay, and we'll do it fast as we did this so we can finish all of them. So you got here arsenic. What is the valence of arsenic? And it would be 5, okay, plus 4 times the chlorine. Okay, you know what to look for the for the valence, right? 4 times the chlorine, which is 7 by 24. Okay, 7 multiplied by 24, it would be 28. Now you have a positive charge here. I don't know if you can look at it. okay? And it's going to be 5 plus 28 minus 1, because if you have a negative charge, you add an electron to the total valence. Let's go ahead and look at the central atom. Sorry for that. I'm going to, a central atom would be the arsenic, right? The least amount, the one on the left, and the one that is less electronegative or least electronegative. So Cl, right? Cl, you don't have to draw the sketch when you do the Lewis structure, please, guys, okay? So you got 1, 2, 3, 4 chlorine, and the total valence would be 33 minus 1, 32, right? 5 plus 28 is 33 minus 1, 32 electrons. So again, you start with the bonds 1, 2, 3, 4, 5, 6, 7, 8. You can do it first, you can do it later, but you just first of all, this is important. You just bond them, you just join them with one lone pair. Then you start to do the other ones, okay? So you got other when you do the formal chart. So you got 1, 2, well, 4, 8. 32 minus 8 is gonna be it's gonna be 4, okay, and it's gonna be 24 left, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you look at it, it's 6 chlorine, 6 6 unshare electron or 3 lone pair. 6 for every atom, and you have 4. Here's the 24. So you got the Lewis structure. Is this the best Lewis structure? Let's look at the formal chart. It is. I know it is already. So let's look at the formal charge of chlorine. You got 7 minus, you got 1, 2, 3, 4, 5, 6 and share plus 1 bond is 7, so it's going to be 0. So each one are identical, and it's going to be, I put it like that, 0, 0, 0. What about the arsenic? The formal charge of the AS would be equal to 5 minus, right, 4, it would be plus 1. Now, what I was saying is, we have to try to get it to 0. Now, every chlorine is 0, and this is positive, not negative. Okay? If you put a double bond, it doesn't make sense, and I'll tell you why. Let's look at it a little bit later. Hold on. You got this. Do we have to have a charge here? Yes, because we have AsCl4 plus 1. We can get, okay, to a 0 total charge, because the total charge would be equal to 0 plus 0, 4 times 0, 3, okay, 4, and then you got 1 positive, it's going to be plus 1. Aye. Let me erase the formal charge here because I'm sorry for that. I'm not going to draw the structure again. And it's going to be plus 1, right? And plus 1. Now, do you have, right? Do you can you do a better Lewis structure? Let me show you, because just in case you are in the exam and you get stuck for some reason trying to do a 0, you will see. First of all, if we put a double bond here for the chlorine, remember what I said about the octet, expand octet only on the central atom. 1, 2, 3, 4, 5, 6, 7, 8. Okay, could be, right? 1, 2, 3, 4, 5, 6, 7, 8. So this, we leave it like that. 1, 2, 3, 4, 5, 6, 7, 8. And by the way, we didn't check 1, 2, 3, 4, 5, 6, 7, 8. Don't forget that I forget when I'm going too fast. Don't forget to check the octet, as I know them sometimes. 1, 2, 3, 4, 5, 6, 7, 8. Now let's look at this. The formal charge of this one we know already is 0. Right? How about this one, this chlorine, which is going to be different? And it's going to be 7 minus how many? 1, 2, 3, 4 unshare plus 2 is going to be 6. and this is going to be a positive here. So here you already know the answer 5, right? The formal charge of AS, arsenic, is going to be equal to 5 minus, okay, let's look at it. How many bonds do you have? 0 lone pair on share electron. 1, 2, 3, 4, 5. Okay, 0. We have a total charge of 0 because it's plus 1, sorry, plus 1, right? Plus 1, this would be 0, and this would be plus 1. 0, 0, 0, 0, plus 1. We got plus 1. Ah, we have the right amount of electron. But what happens here? Can we have in the most electron negative element a positive and here a 0? No. I did it on purpose so you would know, just in case you get stuck on the exam. Okay, so this is the one it works. Let's look at polarity. One, the domains first. 2, 3, 4. So the electron geometry would be 4 atoms, 4 sigma bonds, and 0 lone pairs. So it would be around the central atom. It would be the electron geometry would be tetra. The shape would be tetra too when we have no lone pairs. Now, would it be polar or non-polar? All of the domains are identical, so it is symmetrical, so it would be non-polar. Just remember, symmetrical is non-polar. Asymmetric would be polar. Okay, we're gonna do right now the SO4. We did in class the SO3, I don't know if you remember, but let's do the SO4. It's very similar. The different now we got, sorry, I'm gonna have to. Okay, guys, sorry for that. So we got here, okay, the SO4. Again, let's look at the central atom, which we know already is sulfur. Let's place the oxygens. Okay, I used to do the valence first, but I'm going to place the terminal atoms. That oxygen looks terrible. So it's going to be 1, 2, 3, 4. So you have 6 plus 1, 2, 3, 4. So it's going to be 24, right? Plus 2 electrons, so it's going to be 30, 32. Yes or no? Yes, electrons. So what do? You first your single bonds around the central atom, 1, 2, 3, 8. So 32 minus 8 would be 4. So it's going to be 124 electrons. I'm going to have to do a pause here for a second. Hello? Hello? Okay. Um, So I was on this. If you see that, it's because I'm taking a pause um, on the video, so I keep on going. So we are gonna be here because I'm on Skype too with some students. So every time I get a message, I'll stop it, but you won't notice it different, I think. So, okay, so we have 1, 2, 3, 4, 8. We have to place 24, and we place them around the oxygen, which you know is going to be 6, 4 oxygen by 6 electron each, and share electron each. That makes it the 24. The 24. If you don't believe me, you can double check. So there's no lone pairs on the sulfur. Now we got the same problem here. Okay, let's do for a second the formal charge and check the octets. 1, 2, 3, 4, 5, 6, 7, 8. And you know this has 8 because it's 6 and 2, 8. Okay, so now we go to the formal charge of oxygen, which we already been doing it. So 6 minus 6 on share, right? Plus 1 bond is going to be 6 minus 7 is going to be minus 1. So all of these oxygens are identical. Minus 1, minus 1, minus 1. Let's do the formal charge for the sulfur, okay? For the sulfur. And it would be 6 again, because that's the valence of sulfur, plus 0 on share plus 4 bonds is going to be plus 2. As you notice here, this doesn't look very good, right? So why don't we go ahead and keep on working? Let's, uh,
That's the reason why I do it. And you already know how I said. And let's do minus 1, minus 1, minus 1, minus 1, minus 1, plus 2. And this gives us a total charge of minus 2, which is the total charge of the molecule. Right? We do it excellent, but you don't like that's plus 2. Now, if you move those electrons to the double bond, right, you know that it's going to diminish 1. Okay, I'll do it in part, even though if I'm trying to do it as faster as I can. Okay, I'll do oxygen 1, 2, 3, 4, 5, 6. Because some of you will already put two double bonds that you know that it's going to reduce a central atom to 0. And you can already know that. So 1, 2, 3, 4, we move again the electrons from the oxygen, from the terminal atoms to form double bond on one oxygen. Now, these are going to stay the same. Minus 1 because they stay the same. They have the same amount of unshared electrons. Okay, so you got minus 1, minus 1, minus 1. Now the oxygen with double bond, you know already 0. So it's going to be 6 minus 4 plus 2 bonds. It would be, this is 6, it would be 0. Now let's look at the sulfur. Sulfur, again, this is the oxygen with double bond. So the sulfur would be, the formal charge of the sulfur would be 6 minus, and you'll have 1, 2, 3, 4, 5. 0 unshare and 5, you still got a plus 1. So, okay, now you know how I said plus 1 minus 1 is 0. Plus 0, 0 minus 2, the total charge. I'm adding the formal charge. That's what I'm doing. So if you add them, you can stop here and you can add them. Minus 1, minus 1, minus 2, minus 1, minus 3, plus 0, minus 3, plus 1, minus 2. So yes, you could have known this before, because if you do this, and let's put another double bond here, on the oxygen on the top, it doesn't matter which one. So I move my electrons, a double bond here, I move my electrons, and this stays the same. Okay, this is among here. So now let's do the formal charge. You know that the formal charge for oxygen double bond is 0. And this we know it already. We haven't changed anything here. Now let's look at the sulfur. Okay, formal charge of the sulfur. And it would be 6 minus 0 unshare plus 1, 2, 3, 4, 5, 6. And 6 bond. You see, we got it and you knew that we were going to get the 0 here. It looks like the perfect. Now there's two options that you can go on and put a double bond here. And I'll show you because that is wrong. And I want you to show it because you can even jump and put the double bond here. And that's why you need to do it step by step, even if it's a pain. Let's go ahead and add the formal charge. 0 plus 0. Okay, plus 0 is 0. Minus 1, minus 1, minus 1, minus 2. So we place the electron correctly. Okay, minus 2. And that's the way you represented it. Now let's go ahead and do something. Okay, we're going to do the sulfur and let's put another double bond here. I'm doing it so you would know why this one is wrong. Okay, because you jump and decide, let's put double bond on 3 of them. Or let's put on the 4. And you'll see what is going to happen. This is going to be 0. This is going to be 0. This is going to be 0. And this is going to be minus 1. How about the sulfur now? Sulfur would be, the formal charge of the sulfur would be equal to 6 minus 0 on share plus 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7. Now, I want to make clear that first of all, if you look at this one, let me stop because again I jump it because I knew it. This has the octet. Again, I skipped that. Sorry for that, guys, but you need to do it. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Now you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, sulfur is on the third period. On a central atom, you can have an expand octet, more than 8 electrons. And here, again, on this one too, okay? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can have up to 18. So this one on the octet wouldn't be bad because you got 8, 8, 8. 1, 2, 3, 4. You got here 12, 13, 14. You still are not there. But on the central atom, you're going to have a -1 charge because 6 minus 7. So this is not possible. Again, why? You have a negative formal charge on here, meaning that you have more electron on sulfur, which is less electronegative than the oxygen. So it doesn't make sense that you got a 0 here and the electrons are here. So this is a wrong Lewis structure, not because of the octet. And I wouldn't say wrong, I would say it's not the best. The best would be basically you try to get to 0 or plus or 0 the central atom. Okay, if you cannot get it to 0, stay with the plus because it's the least electronegative element. So let's look at the correct Lewis structure, which was the third one for us. And again, you have, let's look at the electron geometry, e.g. Okay, how many domains? One, sorry, two, 3, and 4. And all of them, right, are atoms. And by the way, let me, okay, erase the formal charges. So you got one here, and one here. You got 4 domains, which is going to be a tetra. And what would be the shape, molecular shape, MS or molecular geometry? It would be 4 and 4, 0 lone pair is going to be tetra. How about the polarity? You got 4 domains and the 4 are identical atoms. Okay? Let me tell you what it means. It's not that it means that you have a domain here with a lone pair. Remember the case we have here, if you went through, that we have 4. We didn't have lone pairs, but one of the atom was different. So there's no symmetry. The molecules is not symmetric, so it is polar. Okay? Remember what I wrote here? It is polar. Okay, so here you have the 4 are oxygen, the 4 are identical atom, so it's a non-polar molecule. And let me see how much do we have here. We have 27 minutes. I'm going to do the last one. Now, I want to make clear that you learn and memorize. You have no choice, the exception. And first of all, you know that from third period down, you can have more on the central atom, more than 8. But at least you have to have 8. Okay? Another thing, at least you have to have 8. Okay? Except for the exceptions. Hydrogen, which is 2. Helium, which is 2. Boron, which is 6, okay? And beryllium, which is 4. Those are the exceptions. Now, carbon is always central. And carbon always have 4 bonds. Now, because carbon hates lone pair is very unstable. And in fact, those are the things that happen when you have, that you study biology, when you have a molecule that is forming a radical, which is called radical because it's going to be a carbon or an element with one unpaired electron, one. So that is producing, like that in some way breaks the DNA and is one of the things that could cause cancer. Okay, so let's go ahead and look at this one. Okay, we got central atom carbon, there's no doubt, and we got 3 fluorine. Okay, again, I draw the bonds. You don't have to draw it first, but we need to be clear. 4 plus 3 times 7 is 21. You got 25 plus 1, 26. So we start with our terminal atoms, placing the lone pairs by pairs, of course. So we got the octet. 1, 2, 3, 4. Let's check. We got 3 plus multiply by 7 is 21 plus 6, okay, it would be 27. Let me see. Hold on. 1, 2, 3, 4, 5, 6 by 3 is 21. By 18, sorry, that's why. 19, 20, 21, 22, 23, 24. We have to put it here. Where are we going to put it? We go to the central atom. Carbon hates lone pair. Okay. So what else can we do? And likes 4 bonds. Okay. So what if we put a double bond here? So we got 2. In here, in this case, you can have the octet on everything, but there's a problem here, and this. Okay? Now we got here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We got the friend. Now carbon has 1, 2, 3, 4, 5, 6, 7, 8. Now count the octet for the fluorine. By the way, if you do the formal charge, this is going to give you 4, it's going to give you 0, 0, 0, minus 1. Perfect. We have all the formal charge. And it makes sense because the fluorine, right, is going to have the negative formal charge. Oh, yeah, perfect. But there's a problem, a big problem here, and some of you notice this already, that fluorine is only capable of having 8, not more. And then beside is a terminal. You cannot have, no way, an expanded octet on fluorine. So you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This cannot be possible. So here we go on a painful exception, which is going to be, okay, you got your fluorines, and unfortunately, you're going to have to place your negative charge on carbon. So you're going to have 2. Unfortunately, lone pair. Even if it hates it, even if it hates the formal charge of 0, of minus 1. So you're going to have 0, 0, 0. Okay, I made a mistake here. Sorry. I should have erased this. 1, 2, 3, 4, 5, 6, 7, 8. Okay, sorry for that. No, no, sorry. I'm gonna have to go back then. You have here 1, 2, 3, 4, 5, 6, 7, 8. But hold on for a second, guys. I know what is the difference. You didn't move the electron. Why? Because you still have, let's say you move the electrons like we did with the terminal atom. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we got 8 by 3, right? It's going to be 24. Okay, and you have, oh, you need 2 more. Where are you going to place them? You have to place them anyway here. Do you see? So this doesn't, this, you would have to place a double bond here, so carbon would have the 4. It's right. The only way you can have this 26 is 2 ways. So you have a double bond having fluorine with 10 electrons, like I did before, or having a carbon with 6. I'm trying to draw the wrong things. That's why I'm sorry. I corrected and things like that because I'm trying to do the wrong thing. And that is wrong because you can. So the only way, like I said, the only way you have your 26 electron and you have a 0, 0, and you have here, right, a negative charge, formal charge. Let me real quick do it. It's 7, the fluorine. 1, 2, 3, 4, 5, 6 plus 1, 7. 7 minus 7, 0. 0 and 0. Let's do the formal charge of the carbon for a second here. And it's going to be, I put minus 1, but I'll show you. It's going to be 4 minus, how many lone pair on share? 2. How many bonds? 3. It's going to be minus 1. Can you have that? What we've been doing, that's what I was gonna get, is, oh yes, you cannot have that because this is more electronegative than the carbon, and carbon shouldn't have lone pair and shouldn't have a negative charge. So let's say I move it over here, okay? Now, okay, you're gonna have here as here's the problem. You're gonna have 0. Yeah, you could have 0 because you're gonna have 1, 2. You're still gonna have a negative. Do you see? And also, this is impossible because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the carbon, you cannot have more than 8. Again, you cannot have a double bond at all. Sorry, I'm erasing. The only possible Lewis structure for this would be an awful and painful exception, which is going to be this one. Having a negative formal charge on the carbon with two lone pairs, which are one lone pair, two unshare electron, which carbon hates it. So you got again, let's look at the shape. Electron geometry would be 1, 2, tetra, okay? But you got one lone pair and three. So it would be electron geometry, it would be tetra, and it would be molecular shape, would be trigonal pyramidal pi. Okay. Is it polar? Yes, it is. Not only for the chart, you can see that it's already um, not symmetrical. Now, I'm sorry for the times that I erased everything. I was trying to show you how bad it would be and how wrong it would be if you put a double bond here, if you put a formal charge of 0 here and a negative. It's not going to work. Ain't going to work, like I say. So it has to be this way, unfortunately, even if this is an exception. This exception is better than the other one, which makes this formal charge negative, how I was saying, and this carbon with lone pairs very unstable. In other words, CF4 is a very stable molecule, but C43 minus 1 is very unstable because it's one exception.